Welcome to qnawire.
So in this problem, we have an insulating solid sphere. And this sphere, we're told, has a radius of 0.12 meters, and it has a total charge of 5 times 10 to the negative 6 coulombs. Then we have an additional small charge of Q equals 3 times 10 to the negative 6 coulombs, and a mass of 6 times 10 to the negative 5 kilograms. And we want to shoot this small point charge directly at the center of this large sphere and see how close we can get. So we shoot it straight at it, and we want to see how fast does this initial velocity need to be in order to get to the point where the point charge is only 8 centimeters from the surface of the large sphere. So since we have an initial and final point, this is a good hint that we're going to use energy conservation. So we simply have energy initial is energy final, and then we have K initial plus potential energy initial is equal to kinetic energy final plus potential energy final. And now we want to think about what's happening here. So if it gets just to the point where it can get 8 centimeters away from this surface, since the big sphere and the point charge are both positively charged, this big sphere is going to be constantly repelling the point charge, so it's going to be slowing it down, and therefore this 8 centimeter mark will be when the velocity of the point charge actually becomes 0. So that tells us that kinetic energy final will be 0. So then also we need to know potential energy of these charges. So remember, we can think of it as potential energy is equal to Q, our charge that's moving, times the voltage difference that it goes through. So now when we plug this in, we have 1/2 mv initial squared plus Q voltage initial is equal to Q voltage final. So now we need to figure out what this voltage is for a large sphere. So remember, if you're outside a sphere, we can pick a spherically symmetric object and treat it as a point charge. So therefore, the voltage outside of this sphere everywhere will simply be equal to the voltage from a point charge, which is just the total charge divided by 4 pi epsilon naught times the distance you are from the center of the sphere. So plugging this in, we have 1/2 mv initial squared plus little q times big Q over 4 pi epsilon naught. And now we need to find the initial distance. So that initial distance, we're just going to call our initial for now. That's 1 over, which is equal to Q times big Q over 4 pi epsilon naught, our final. Okay? And now what we're trying to find is this initial velocity that we have to shoot this object with. So one thing to notice is that if we have Q over 4 pi epsilon naught our initial, well, we're told initially the object is starting very, very far away. So we can treat this as kq over 4 pi epsilon naught times infinity, or in the limit as our initial goes to infinity, and this just becomes 0. So now our equation simplifies immensely. We have 1/2 mass times initial velocity squared is simply equal to kq over 4 pi epsilon naught times R final. And then remember, R final has to be measured from the very center of the large sphere out to the point where it is. So R final will be equal to the radius of the large sphere plus 0.08 meters, which will simply give us 0.2 meters. So now, solving for V initial is equal to the square root of 2q over 4 pi epsilon naught m times RF. And when you plug in all the given values in the problem, you just find that V initial is 150 meters per second.